This video is for Math 116, and this is for section 4.1 on combinatorics and the fundamental principle of counting. So combinatorics, I think, is a really interesting area of mathematics that gets kind of introduced sometimes in, like, I learned about permutations and combinations in a pre-calculus course in high school. Let's see, I took a coding, well, it was called algebra coding, and it was a discrete math course that was focused on the codes that computers use that are used to run computers, how computers communicate back and forth to each other using binary codes, and how you can have check processes in those codes to make sure that none of the bits have been changed from a 0 to a 1 or vice versa. That's really interesting stuff, and that was what was going on at Bell Labs back in the 1950s as the digital computer world was being born after World War II. Let's see, what else? I took a discrete math course a while later. Anyway, all of these things generally come back to some of these elementary ideas that we're going to talk about in Chapter 4. The fundamental principle of counting, I think, is an excellent place to start. Then we'll talk about permutations and combinations, and then we'll maybe look at using some of these ideas to calculate probabilities. Let's see. Oh, an area that we don't get to, that's what I was kind of thinking of, which is, and I want to talk about it because I find it really interesting, and I didn't study it in a course. I learned about it really on my own. And these are numerical systems that are called modular systems, or they use modular arithmetic. Sometimes I found it in one high school textbook what they called clock arithmetic, where if you, let's say it's 6 o'clock and you add 10 hours to it, then at least in America you don't say it's 16 o'clock. You have to subtract the 12, and so you would say that it's 4 o'clock. And so it's all about remainders. And these modular systems are really, really interesting things. They drive computer security. There's what's called a Diffie-Hellman key exchange, which is very important in cryptography. And these are mathematicians and computer scientists who were developing these methods back in the 1970s. And then there's the RSA crypto system. Ron Rivas, I forget his first, Avi Shamir and Adelson. I can't remember their first names now, but anyway, these were three mathematicians who developed this crypto system. And then also the blockchain technology that controls most cryptocurrencies. These are concepts that were developed by Neil Koblitz. I'm not sure if he was at the University of Washington when he did that, but he just, I'm not sure if he's retired or he's professor emeritus or what it is. Anyway, he's a pretty old guy who taught up in Seattle at the University of Washington for many, many years. And he developed these concepts that are used in blockchain technology as well as cryptocurrencies. And this all falls under the category of discrete mathematics. It's really, I think it's really, really interesting stuff. Okay, so that's a little introduction to the concept of discrete mathematics and combinatorics. So the fundamental principle of counting is pretty straightforward. If you have one thing that can be done X ways and a second thing that can be done Y ways, then the number of ways to do one after the other is X times Y. And this becomes really clear when you draw a tree diagram for one of these scenarios. For example, let's see if I find this in the textbook. Well, a good one to do is if you roll a die, 6 sides, and then flip a coin. Okay, so 6 ways for this one to happen, 2 ways for this one to happen. So here's our tree diagram. You could get a 1, a 2, a 3, a 4, a 5, or a 6. And after each one, you could have a heads or a tails. So you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 possibilities, 2 times 6. Okay? It's a pretty straightforward concept. Now the thing about this, and this is true of a lot of mathematics, but I think it's especially true in combinatorics, is that we study these concepts and these sort of methods of determining answers in isolation. The really challenging problems are problems where you've got to choose, well, is this a fundamental principle of counting problem, or is this a permutation problem, or is it some weird combination of the two? Because that is what is most common. But anyway, so we'll talk about these in isolation, and then later in the chapter, if we have time, we'll look at some more sophisticated questions. So this example, I'm going to do one more tree diagram. On page 123, we've got this ice cream shop that offers vanilla, chocolate. Oh, I'm going to need to leave myself plenty of room here. So let's see, vanilla, chocolate, well, going to need room there too. Chocolate, strawberry, boysenberry, and Rocky Road. Okay, so, and then we have waffle, sugar, or wafer cones, right? So, waffle, sugar, or wafer. So let's see, I'll call this WF and that one WR. Waffle cone, wafer cone. So then they all have these 3 possibilities for the cone. Okay. And then the last choice is plain or with sprinkles, right? So, plain or with sprinkles, plain or with sprinkles, plain or with sprinkles. And then they all have all of those possibilities. Okay, so you've got 5 different flavors of ice cream, 3 different possibilities for the cone, and then 2 choices for the sprinkles. And so there's 30 different possibilities. You can see each flavor gives us 1, 2, 3, 4, 5, 6 possibilities. We've got 5 different flavors, so there's our 30 different possibilities. I'm not going to count all 30 of them. Okay, so there's the basic ideas for the fundamental principle of counting, what a tree diagram is, and why it can sometimes be helpful. So let's look at the problems. Over on page 125, problem 2, we've got a local telephone number consisting of 7 digits. Given that the first number cannot be a 0 or a 1, all right, so we've got 7 digits. This one cannot be 0 or 1, but that's the only restriction. How many different phone numbers then are possible? Okay, well, there are 8 single-digit numbers, 8. Well, there's 8 for this one. There are 10 to start with, okay, 0 through 9. So there are 10 single-digit numbers, the numbers 0 through 9. If we're not able to use 2 of them, there are 8 left, okay? And then we've got got 10 choices for each of the other positions. So we've got 1, 2, 3, 4, 5, 6. So that's 10 to the 6th power. 8 times 10 to the 6th. Or 8 million different phone numbers, okay, without an area code. All right, problem 3 gets a little bit more into what happens when you introduce an area code, restrictions on the area code. When I was in high school, all area codes had a middle digit of 0 or 1. And that has to do with the way the phone company set up their switches. But they changed that. So by the 1990s, there was a lot more freedom in how you could create an area code. And that's where we got like the 541 area code is a pretty new one. If you look at all the old area codes like 503 and 206 and 415, they all have a 0 or 1 in the middle, and you can tell the newer area codes because they don't have a 0 or 1 in the middle. Let's see here. What else was I going to say about that? Okay. All right. Well, let's go look at problem 4. So, problem 4, a coin is flipped 5 times, and each time, the result each time is recorded. How many different possible outcomes are there? Okay, so we're flipping a coin 5 different times. Every time we flip it, there are 2 possibilities, heads or tails. Okay, so this would be 32 possibilities. You could, I'll start a little tree diagram here so you can see where this is coming from. Okay, let's see. What do we got? 1, 2, 3, 4, and then one more setup here. And this will probably be 16 of the possibilities. I'm running out of space here, that's why. When you make a tree diagram, you got to make sure that you've got plenty of space for these last sections. So, there's 1, 2, 3, 4, oh, I'm losing my place here. But I think that was 4, and then 5, and 6, and 7, and 8, yep. Let's see here. I think that's all of them on that top half, and then 9, and then 10, 11, 12, let's see, 13, 14, 15, 16 possibilities. And if you write them all out, you know, there's H, 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 T, and then H, 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 T, H, 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 T, T, and so on, okay? So, you know, sometimes you might want to see all the possibilities written out, listed out. Sometimes it's helpful to see it in a tree diagram. Sometimes you just want to know how many there are, okay? All right, so let's see here. Problem 6. 2 cards are chosen from a deck of 52 cards. So this is just a method that I use when I'm doing these problems, right? The fundamental principle of counting says if one thing can be done in X ways, something else can be done in Y ways, then the number of ways they can be done together is X times Y. And we can extend that if we're doing something 5 times, right? Then we'll be multiplying it, multiplying something by itself 5 times. In problem 2, right, we had the phone number where there were 7 digits and there were, you know, so many possibilities for each of those positions. And so the idea is I just fill in, you know, how many possibilities are there for each place and then multiply them together. So problem 6, let's see. The first card is not replaced before the second card is chosen. How many ways can we choose a spade first and a heart second? Well, there's 13 spades in a deck of cards, and there are also 13 hearts. So there's 169 different combinations of ways that we can pull a spade and then a heart, right? So for the spades, you could have a 1 and then, or an ace, right? And you can have that together with the ace of hearts. Or you can have the ace with the 2 of, there we go, 2 of hearts. Or you can have the ace with the 3 of hearts all the way up to the king of hearts, right? And then if you've got the 2 of spades, then you could have the ace of hearts or the 2 of hearts, and so on, okay? So that's what this is delineating, is that there are going to be 169 possibilities like this. Each of the 13 spades can be matched up with each of the 13 hearts, and that's where we get 169. Now, if you're going to draw 2 spades in a row, if you don't put the card back in the deck, then there's only 12 left when you draw the second one, right? And so in this scenario, if you start out with the ace of spades, then there's only going to be 12 possibilities left because you already have the ace, right? You could have the 2 or the 3 or the 4, but not the ace again. And then if you draw the 2 of spades, well, you could have the ace or the 3 or the 4, but you can't pull the 2 again. And so that's where we get 13 times 12, and that'll be 156 possibilities. Okay, let's see here. Problem 8, baseball team has 7 pitchers and 3 catchers. How many different pitcher-catcher combinations are possible? Pretty straightforward. It's 7 times 3, so there's 21 possibilities. Okay. Something that I didn't put into this problem set is sort of and we get into this in other later in the chapter, like on a basketball team. You know, if you have, let's say you have, 5 guards on the roster and, 5 forwards on the roster and 3 centers, how many ways can you choose 2 guards, 2 forwards, and 1 center? Okay. So there are ways to calculate this. You have to take into consideration, and that's why we covered in the later section of the chapter, right? You have to, guard A and guard B is the same as guard B and guard A, so you don't want to double count that. But what's really interesting is obviously some players can play both guard and forward, and some players can play both forward and center. And so when you start trying to delineate those possibilities, that's what I was saying before about how we study these methods for combinatorics, but when you try to apply it to problems, frequently you run into situations that don't fit into these neat little boxes, and we kind of have to adapt our methods to what's going on in the problem. This is a very straightforward problem, okay? We'll see those more complicated ones later on in the chapter. Okay, so that was problem 8. Problem 10, combination lock is numbered from 0 to 30, so that's 31 possibilities. Each combination is 3 numbers in succession. The successive numbers must be different, but the first and third can be the same. Okay, so for the first one, we've got all possibilities, 31 possibilities. Then, after you've chosen a number, you can't use it again, so now there's only 30 possibilities. So here's where it gets interesting. Now, for the third number, you can't use the one that came second, but now the one that came first is available again. So now there were 29 possibilities, but we add one back on, and so it's 31 times 30 times 30, and that's going to be what? 20, what is that? Because 30 times 30 is 900, and then I was trying to do that times 31 in my head. Oh, 27,900. I wasn't shifting my place values correctly to get that 900 in there. Okay, so that's it for section 4.1. Like I said, this is kind of an introduction to these concepts. Fundamental principle of counting is pretty straightforward, and we will kind of build up in complexity as we move through the chapter. As always, if you have any questions, please let me know. Thanks.